Hi everyone! Today we're going to discuss the chain rule. The chain rule kind of combines all the rules we've been doing so far, so we will be using the power rule, rules for e, rules for ln. Remember that the derivative gives us how a function is changing. So we can see in the graph of f of x equals e to the negative 2x that the function is decreasing. So what would we expect our derivative to be? Would it be positive or negative? Hopefully you're thinking that the derivative should be negative because we can see this function is decreasing. It is going down. But the only thing we know so far about e to the x is when we take the derivative, we get e to the x. So we need a new rule that talks about, well, what happens if I have something other than x in the exponent? Today we're going to have that e to the u, where u is a function of x, has the derivative e to the u times u prime. This new rule needs to be added to your list of derivative rules. So let's find some derivatives. Given f of x is e to the negative 2x, when I take the derivative, I will write down again e to the negative 2x. Then I look at the exponent, negative 2x, and I take the derivative. So those are my two parts. I rewrite what I had, then I just grab the exponent, take the derivative. This derivative then is e to the negative 2x. Derivative of negative 2x is negative 2. This negative 2 is why we can see the function is decreasing. We can rewrite that one more time. Bring the negative 2 in front, e to the negative 2x. Now let's plug some numbers into the derivative. So let's start with f prime of 0. I have f prime of 0 is negative 2 e to the negative 2 times 0. Well, we know negative 2 times 0 is 0. E to the 0 is 1. Our derivative is negative 2. Let's try f prime of 3. F prime of 3 will be negative 2 e to the negative 2 times 3, which is negative 2 e to the negative 6. So let's practice our rule, and let me write it again for you. Our rule is e to the u. When I take the derivative, it's e to the u again times u prime. F of x is e to the 12x. The derivative will be e to the 12x. I repeat what I started with. The derivative of 12x is 12. I'm going to rewrite that as 12e to the 12x. Number 2, g of x is 4e to the 3x minus 5. G prime of x will be 4e to the 3x minus 5. The derivative of 3x minus 5 is 3. I can combine the 3 with the 4 and get 12e to the 3x minus 5. So the new thing you're having to do is to remember, once you rewrite your function, take the derivative of the exponent. 3 says y is e to the x squared plus 3. Y prime starts e to the x squared plus 3. Then I look at x squared plus 3. Derivative of x squared is 2x. Let's rewrite that as y prime is 2x e to the x squared plus 3. 4 says capital F of x is equal to 7 times e to the 2x. F prime of x will be 7. E to the 2x, derivative of 2x is 2. Because I can, I'm going to multiply the 7 times the 2. I have f prime of x is 14 e to the 2x. A little bit bigger, h of x is 6e to the x squared plus 5x minus 3. H prime of x will be 6 e to the x squared plus 5x minus 3. So every time I start, I'm just rewriting what I had to begin with. Then I'm looking at the exponent. X squared plus 5x minus 3 is 2x plus 5. There's no need this time to distribute. I have two terms. You could multiply by the 6, but it's really not necessary. We'll stop right here. Let's try g of x is 9e to the negative 3x. G prime of x is 9 e to the negative 3x, then I take the negative 3x, derivative is negative 3. 9 times negative 3, negative 27 e to the negative 3x. So those were all e. Let's talk about what happens if we switch that from e to a different number, and I'm going to call that different number b. So if I have b to the power u and I take the derivative, I'll have b to the u, I'll have u prime, and I'll have the natural log of b. What we're going back to is we had b to the x. When we did the derivative, we had b to the x natural log of b. So the addition of changing it to a u, where u is a function of x, means we'll have to take the derivative of u as well. So it kind of feels like 3 steps. Those 3 steps is why we call this the chain rule. I have the first part, and then I add a part, and then I add another part. I know I'm not a good drawer, but it shows you the idea of a chain. A chain has links. So the b to the u gives me a link to the exponent, take the derivative, and then the base, use the natural log. So you see those pieces starting to pop up. And why we call this the chain rule? Because it has a bunch of parts to it. So let's start with 6 to the 4x minus 5, and we're taking the derivative. So I start with what I had, 6 to the 4x minus 5. I'll write it the long way. Derivative of 4x minus 5, and then the natural log of the base, which was 6. So I have 6 to the 4x minus 5. The derivative of 4x minus 5 is 4, and then I have the natural log of the base, which is 6. If you wanted to, you could write the 4 in front, but you can't combine the 4 and the 6. They don't multiply. I can't do anything with the natural log. It doesn't multiply to combine terms. So this is the answer. So even though it looks big and it looks like a little pieces, that's exactly what you're supposed to have. We'll start with f of x is 8 to the 2x. To take the derivative, I start with 8 to the 2x. The derivative of 2x is 2. I take the natural log of the base, which was 8. G of x says 5 to the x squared plus 4. The derivative starts with 5 to the x squared plus 4. The derivative of x squared plus 4 is 2x, and then I have the natural log of the base, which was 5. 3 says h of x is 9 to the x cubed plus 4x squared minus 5x minus 3. H prime of x, I start by rewriting the whole thing. 9 to the x cubed plus 4x squared minus 5x minus 3. I take the derivative of the exponent. X cubed becomes 3x squared. 4x squared is 8x, minus 5x is negative 5, and the 3 drops. Then I take the natural log of the base, which was 9. Now that we've talked about e to the x and b to the x, let's go back to the natural log. Our rule before said if I have the natural log of x and I take the derivative, I get 1 over x. Now I'm adding u, which is a function of x, so I have to look at how to do the derivative. So the chain rule says the derivative of natural log of u is u prime over u. So the u goes in the bottom, the derivative goes in top. What I'd like to think about is if I see natural log, I know my answer is going to be a fraction. All right, we'll start with f of x equals the natural log of 4x minus 2, the derivative. I put 4x minus 2 in the denominator. 4x minus 2 goes on the top, and I take the derivative. The derivative of 4x minus 2 is 4. Then I keep 4x minus 2 as it was. This particular time, 4, 4, and 2 are all multiples of 2, so I could reduce this to 2 over 2x minus 1. Let's try a few more examples. I have f of x is the natural log of 5x plus 3, f prime of x. I put 5x plus 3 in the denominator. Derivative of 5x plus 3 is 5, and I'm done. Before we had rules that said if I have the natural log of a product, I had to expand it, or if I had a power, I had to bring it down. But now with this new rule, I can kind of tackle this all at once. I'm going to say y prime is equal to the 8x cubed goes into the bottom, and then the derivative is 24x squared that goes on top. I can see then I have powers of x's that can cancel. So x squared on top, x cubed on bottom leaves an x on the bottom. 8 goes into 24, I can put a 3 on top. Now this is the same thing we would have got if we had expanded, and let me show you that. I could have made this the natural log of 8 plus 3 times the natural log of x. Remember, the multiplication becomes addition, the power comes down. If I did the derivative this way, natural log of 8 is a constant, so the derivative is 0. Then 3 ln of x, I would keep the 3, the x would go on bottom. So you can see I got the same thing. I got 3 over x both ways, but the second way, using the chain rule, goes a bit faster. Number 3, g of x is the natural log of 7x squared plus 9. To do the derivative, remember I'm going to take that 7x squared plus 9 and I'm going to put it into the bottom. Then the derivative of 7x squared plus 9 is 14x. I take a quick look to see if I can reduce, and I can't. 7, 14, and 9 don't have any common factors, so I say that one looks good, and I go to the next one. Here I have the natural log of 8x plus 1 over 3x minus 2. Now in this case, I do say it's important to expand it. What I do not want to have to do right now is the quotient rule, right? I don't want to have to put the 8x plus 1 over 3x minus 2 in the bottom and do the derivative on top. So instead, I'm going to say this is natural log of 8x plus 1 minus the natural log of 3x minus 2. So yes, I'm being picky. Yes, I'm deciding when should I use the rules for expansion and when don't I? Well, I expand it if it makes my work easier, and I don't if it looks too hard or if it's not needed. So this time, I don't want to have to do the quotient rule when I'm doing the derivative, so I expand it instead. H prime of x will have two parts. The first part looks at 8x plus 1. It goes in the bottom. Derivative of 8x plus 1 is 8. Now I subtract. Natural log of 3x minus 2, the 3x minus 2 goes into the denominator. Derivative of 3x minus 2 is 3. And you can stop right there. We don't need to have a common denominator. We don't need to combine anything. We just say, that looks great, and we keep moving along. Number 5 says the natural log of 6x squared plus 1 to the 2/3. Now, I do want to start this one by bringing the 2/3 in front and then having the natural log of 6x squared plus 1. Let's go ahead and call that y, so I have something to write with it. What this did, it kept me from having to do more work later. So I'm bringing the 2/3 in front because it's a power, and then I can take the derivative. So I'm going to say y prime is equal to, let's write the 2/3 first. Then the 6x squared plus 1, I put that in the bottom. Derivative of 6x squared is 12x. I put that in the numerator. I can simplify this a little. I can say 3 goes into 12, and that gives me 4. Then 2 times 4 is 8x over 6x squared plus 1. I can't do anything with the 6x squared plus 1 because of the plus 1. It would have to work for both things. In 1 and 6, the only common term they have is going to be 1, so there's no simplifying for the denominator. So what if we had the log base b of u? Well, remember, our rule for the log base b of x, when we took the derivative, was x natural log of b with a 1 in the numerator. So it's going to change kind of like you would expect. We're going to have u, natural log of b in the denominator, and u prime in the numerator. So it looks a lot like it did for natural log, but we have that addition of the natural log of b. So my first example is f of x is the log base 2 of 9x cubed when I take the derivative. I'm going to start with just grabbing the 9x cubed and put it in the denominator. I'm going to put the natural log of 2 because that was the base. Derivative of 9x cubed is 27x squared. 27 over 9 is 3, so let's simplify and put 3. X squared over x cubed just becomes x, and I have natural log of 2. So let's try that for a couple more. First one says log base 4 of 2 plus 5x. Let's call that y. So y prime, I'll have 2 plus 5x. Let's put that in parentheses in the denominator. I'm going to put the natural log of 4, which was the base of my log. And in the numerator, 2 plus 5x, the derivative is 5. Nothing simplifies. Same thing, if I'm looking at y equals the log of 4x squared. Well, remember, when we don't write the log, it means it's base 10. Y prime, I make a fraction. The 4x squared goes in the denominator. I attach a natural log of 10. 4x squared derivative is 8x. This one simplifies. 8 over 4 is 2 in the numerator. X with x squared in the denominator gives me an x, and I have the natural log of 10. So now we're ready to talk about the generalized power rule. Before we had the power rule, f of x equals x to the n, gave us the derivative of n x to the n minus 1. So instead of having x, we have u. U is just going to be some kind of function of x. When I take the derivative, the same kind of thing happens. So the n comes down, just like before. I change the power to n minus 1. That feels normal. The new part is to do u prime, but we saw that with e, we saw that with b, we saw that with log, so it should feel kind of familiar by now. But let's look at it, start to get a feel of what that's going to look like. So my first example, I have f of x is 4x plus 3 squared. The derivative, f prime of x. The 2 comes down. I have 4x plus 3. The new power is 1. Then I attach the derivative of 4x plus 3, which is 4. So the power came down, like we expect. It reduces 1. But now you're going to have to go back inside to the 4x plus 3 and give the derivative. Now we could have done this the long way. We could have expanded f of x and made it 16x squared. 3 times 4 is 12, so we would have 24x plus 9. So we could have distributed. Then we could apply the power rule, which would say 32x plus 24. But that's what we got by doing the chain rule also. If I look, 2 times 4 is 8, so I have 8, 4x plus 3, which you could see if I distributed 8 times 4, that would give me 32. 8 times 3, that would give me 24. It's better, it's easier to do the chain rule because powers are going to get bigger, and as powers get bigger, we are not going to want to expand. Let me show you what I'm talking about. Look at this 8x minus 5 to the power 6. No way we want to do that. We don't want to expand it. So instead, we'll use the chain rule. The chain rule says bring the 6 down, keep 8x minus 5, but now it's to the power 5. Then inside 8x minus 5, the derivative is 8. 8 times 6 is 48, so I have 48, 8x minus 5 to the power 5. This is how we want to do it, so it makes it easier, pretty short. Just remember to attach the derivative after. It's going to take a while to get used to. You're used to doing the power rule. This is very similar to the power rule, but you got to remember to put that little part at the end. What I like to think about is when I look at a problem, what rule am I going to use? And if I think chain rule makes me think there's pieces. So those pieces are the 6, the 8x minus 5 to the 5th, and the 8. So seeing those 3 pieces makes me think, oh, I've done multiple parts. I've done the chain rule, which was what I was supposed to do. So let's try g prime of x. The 4 comes down. I have 7 minus 3x squared. And now it's to the power 3. So the 4 came down, it drops 1, it's 3. Inside 7 minus 3x squared, the derivative is negative 6x. I want to put these two pieces together, the 4 and the negative 6x. So I have g prime of x is negative 24x, 7 minus 3x squared, and then cubed. So you really have to pay attention to order of operations and what you're allowed to combine and not allowed to combine. Things without powers, like the 4 and the negative 6x, you can multiply those together. The 7 minus 3x squared has a power 3 attached, which means you're not going to touch it. We're not going to expand to the power 3, so we're not going to be able to put those terms inside with the parentheses, but that's okay, we don't need to. We really want to get things into factored form as we go, so this is a really nice way to look at the problem. So our next one says 4x minus x cubed to the power 8. H prime of x. I'm going to start with the power. It comes down. So I have 8 times 4x minus x cubed didn't change. I drop it to the power 7. Inside, derivative of 4x is 4. Negative x cubed gives me 3x squared. This time I'm going to leave it alone. What I usually end up doing is multiplying monomials. So a number or a number with a power. But once it gets up to binomials or trinomials, I tend not to multiply those out. I leave them as each individual factor. So I have 3 factors here, 8, 4x minus x cubed to the power 7, and then 4 minus 3x squared. Number 4, the chain rule really comes in handy because we don't have any way to distribute or simplify the square root. So we wouldn't be able to take the derivative of this kind of function of the square root of x squared plus 2x minus 5 unless we went way back to the definition of derivative, which we all know we don't want to do. So here what I can do is I want to think about the square root as power. I have x squared plus 2x minus 5, but remember now the power is a half. When I take the derivative, f prime of x, the half comes down. I have x squared plus 2x minus 5. When I subtract 1, think 1/2 minus 1 is negative 1/2. So be careful with your exponents, especially when they get different, like negatives or fractions. You want to be super careful. Derivative of x squared plus 2x minus 5 is 2x plus 2. Okay, lots going on here. First, let me point out I have a 1/2 and I have 2x plus 2. Those two things I can simplify because 2x and 2, both multiples of 2, I could put that together and make that x plus 1. The negative 1/2 says, well, that really belongs in the bottom and it's a square root. So I'm going to write that as x squared plus 2x minus 5. This is f prime of x. Is it 100% necessary to do that? Not really. But what's going to happen, I keep saying, like, what's our goal? Our goal is, after we learn all the derivative rules, is set things equal to 0. With fractions, I've told you before, you can only set a fraction equal to 0 where the numerator is 0. But I need to know what the numerator is. So by putting it back in this form with x plus 1 over the square root of x squared plus 2x minus 5, it puts everything in perspective. So I can tell that x plus 1 is the only thing on top. It would be 0 when x is negative 1, and I really wouldn't have to worry about that x squared plus 2x minus 5 in the denominator. Let's look at this one. G of x says 10x plus 3 to the negative 2. So now we introduced a negative power, g prime of x. The negative 2 is going to come down. Keep 10x plus 3. Remember, when you subtract, negative 2 minus 1 is negative 3. Don't forget to go back into the 10x plus 3 and make that derivative 10. Now, negative 2 times 10 is negative 20. I'm going to first write it as 10x plus 3 to the negative 3. And then just again, as that habit of thinking about what's really going on here, I'm going to put the 10x plus 3 cubed in the denominator. So both of these equal, you pick which one you want to write. H of x is very similar. I have 1 over 4x minus 9 squared. What you have to do is think, let's rewrite that as 4x minus 9 to the negative 2 power. So when you first looked at h of x, it looked like a quotient. But when the numerator is a constant, so here I had 1, I can rewrite it as just an exponent. So I make it a negative exponent and I avoid doing the quotient rule. I do the derivative. Negative 2 comes down. I have 4x minus 9. Remember, minus 1 gives me negative 3. Inside, derivative of 4x minus 9 is 4. 4 times negative 2, there's negative 8. I'm just going to go ahead and put the 4x minus 9 cubed in the bottom. Right, so it's back in the same place. This video is about the rules. There's one more video. It's going to be also about the chain rule, but it'll be more examples and I'll have some word problems, show you some application. So make sure you go back and watch it.